Okay, I would like to be speaking about conscious consistency with CRDTs in Akka Cluster and distributed data. This is because akka-distributed-data in 2.5 is going to hit stable, and I think it's going to be a great breakthrough in what you can do to your data, and maybe let me talk about that in my talk. Who I am? I'm a vintage retro lover, and I'm Akka contributor. This is one of my contributions, one of my pull requests, on the way to have deltas in the CRDTs for the 2.5 release. Okay, so a short roadmap, CRDTs. First I'm going to start talking about why CRDTs are important, because that's missing from most of the CRDT talks. Then I'm going to talk a little bit about mechanics, but less than usual, and then in Akka. So maybe let's start with why. Okay, CRDTs, maybe let's start with actually talking about this acronym. C stands for, okay, in a minute. R stands for replicated, which means that there is some cluster, idea of cluster, of nodes. It's a distributed system. Every system nowadays is a distributed system, so CRDTs looks like something usable there. And replication, okay, so cluster will need only to provide very low-level primitives, nodes and communication like RPC, which actually Akka Cluster does. And there will be a replicator. I will talk about replicator later. DTs stand for data types. All right, no, that's kind of obvious. And what C stands for? Okay, so this is from Peter Bailey's highly available transactions paper via the always excellent author post. This is hierarchy of consistency. The right side may be less interesting to you because it's about classic databases, because it's what happens when you have two objects and you want to do a consistent update to those two objects at the same time. So it's like repeatable reads and all the stuff. This is more interesting for us when we deal with distributed systems, is what happens to an update on a single object. That's one of the most important slides, I think, in this presentation. So basically, the red is very good from semantics point of view because it's just linear programming, the one we are used to. It's like we have one computer, we can do something to it. And this green thing is something that is always available. So like weird things are here, okay? These are the names of consistency guarantees. This is linearizable. So there is one linear history of everything that has happened. And this is, if you did everything on a single computer, that what would you get? And sequential is almost the same, actually. And from the CAP theorem, we know that this is consistent, because this is exactly what's the definition of consistency in the proof of CAP theorem. But it means that it cannot be highly available. So it means that, for instance, if you're going to get a cluster spanning the whole Earth, like a traditional cloud solution, like you would like to be available in every geographical place, then you would have to take a hit on the round trip through the Earth. For mobile solutions, it's absolutely no-go because some of them can be permanently unavailable. Okay, the green area is just always available, but not maybe consistent. And this is very interesting because what is here is causal consistency guarantees, read your rights guarantees. So if you think about what your system would be giving you, is like read your rights is probably a sane thing. I wrote something, I would like to read it. Causal is also important. I did something to my data, got a side effect, and then after that, I wouldn't like to get, you know, a change of the data after I read a variable. So in my program, I just write something and I read something, but actually in the storage, it gets written after I read it, which is going to be weird. All right, so this is pretty sane. So CRDTs C stands for concurrent, okay, because we would like to get in the green area of highly available things. So our updates should be concurrent. So we would like to allow concurrent updates on the cluster nodes without requiring synchronization. So get AP system, basically. To get high availability, high throughput, perfect for like shopping cart for like worldwide library, like bookstore, like Amazon is, or maybe for mobile devices. But looking at this this diagram, so red area is absolutely no-go. So maybe here, okay? So maybe CRDTs here, or maybe CIDTs here. No SQL is here. If you read Author, you'll know that Mongo is in the green area. I don't know if green is good. Let's see. Well, actually, it turns out that green is not good. Here are anomalies, okay? And we actually don't want to be here with CRDTs. Let me show you why. This is from paper on OR set, so optimized conflict-free replicated set. And this shows nice anomaly of Dynamo shopping cart, which Cassandra, the old Cassandra, is based on. Basically, on one side, on one replica, so one node, I add E, one book, and then I add F, another book. Then I add G on this side, and I remove E. I don't want this book anymore. And after synchronization, I get E back. But no worries, Dynamo paper says, shopping cart service, 99.94% of requests just saw one version, which I read as 600% has seen at least two versions. So 6 out of 10,000 cases where we ship a book that hasn't been paid for. It's okay for Amazon. It's part of the business, okay? It would be good to be aware about consequences if you're building a it's like trading system that would deal in large volume transactions, like billion of monetary units, and you wouldn't like to get 6 out of 10,000 cases duplicated, because then you'll be very quickly out of business. Okay, so we don't want to be here, we want to be here, and CRDTs are actually here. Why this is blue? Because there is a price to be paid to be there. It's not as costly as here. You don't need to synchronize, but there is some price to be paid. Okay, so the price to be paid is you need to be convergent and conflict-free. Any two replicas must converge to the same state after updates have stopped, which is eventual consistency, but with a twist. And conflict-free means that state change is incremental. No historical state can be changed. So if you have ever resolved a conflict, it stays resolved forever, which is not the case with NoSQL solutions. And that's why they try shipping solving conflicts to the client library. It's what React does. It says, I have a conflict, can you solve it for me? And well, that's a bit of a problem, because you usually don't know how to solve this conflict. So CRDTs contain rules for solving conflicts if that's necessary. All right, what and how? Let's start with the simplest CRDT. It's growth-only set. It's growth-only set. It has the API has just two operations: add an element and get all elements. It doesn't allow for removals. Removals are a problem, but we can deal with them in a minute. This is gset's timeline. So let me stop for a while. X is our gset, is this object. These are instances on cluster nodes, okay? And on one node, I'm adding A. On other node, I'm adding B to the same gset. What happens is the updates get replicated. So the A from here goes to here, the B goes here, so like this is causal history, is causally consistent. So first B goes here, and then A goes here, and then I get A and B. The B goes here, and I get A and B, and here I just didn't get an update from here yet. It's eventually consistent, so I have only B. Okay, it's eventually consistent, but there are clever solutions for that problem. But yes. But it's eventually consistent in a disciplined way. So in the end, I got A and B, and then A and B. I could get B or A, but I couldn't get C anywhere. So I don't get a like unwelcome update. And there is a causal history here. That's based on the comprehensive study on CRDTs, which is very nice, like 50 some pages. Okay, so GSet, 2 operations, no removals. Update is merged with existing set with standard set union operation, as you've already seen that. And what's an update? Okay, an update contains the full state of GSet. Why? Because of a causal history. So to support the causal history, we need to give you the full update of a GSet, which is actually not the case for GSets, because GSets have just elements, and if I add something, it'll get added. So I can add them in any order because it's a set, and this is why for GSet, delta updates are very simple. You just ship the elements instead of full sets, and everything works fine. The other thing is merge is set union, and set union actually is commutative, idempotent, and associative, which means that commutative means I can apply updates in any order, because when I'm out in the network, I'm not sure about the order. The network doesn't guarantee me any order. Idempotent, which means if I do an update twice, the result is the same, because to get something really done in network, if I should be repeating, because packets could get lost. And associative means that I can apply the operations in any order. And this is no accident, because those properties are really needed for the distributed cluster to be giving you consistent results, because network is exactly like that. So you need an operation that's commutative, idempotent, and associative, like addition, unlike what? Subtraction, division, okay? That's a problem. That's why GSet is only for addition. But we'll overcome it in a second. All right, which technically is called that GSet is a monotonic joint semilattice object. A monotonic means I'm shipping the whole state, which is increasing historically, so there is some causal relationship. And joint semilattice object is something that has a merge operation that calculates least upper bound of source states, which for GSet accidentally is smallest set containing all updates, which is actually the set union of all updates. So saying this semilattice thingy means that I would actually to have a least upper bound operation, which actually means that this should be something commutative, idempotent, and associative. And if I can find such a property that's incremental and that has this least upper bound operation, then I'm fine, because network will not break me and my object will be CRDT. So whenever I can prove it, that my creatively engineered, crafted, handcrafted operation is actually that thing, that I'm fine to go. Aji Counter. So how to count in a CRDT compliant way? I would like to have 2 operations. I forget about subtraction. In a minute, we'll get to the subtraction. I have 2 operations, increment and get value. That's obvious, like G said. But that the merge is actually tricky. Because imagine I have done an update on 2 nodes of a G counter. So on one, I just added 1, and on the other one, I just added 1. Now there's a problem. What should be the least upper bound operation? Should it be something related to addition? Might not be good, because I've added this on this node, and I ship it to the other node. So I ship it from node A to node C, and I ship it to node B, and node B ships it to node C, okay? So I got update twice. Not good, although addition is commutative, associative, and idempotent. Maybe a maximum operation could do the trick. Because maximum of 1 and 1 would be just 1, okay? So it doesn't depend on how many times I get it. But it's still not going to be enough, because then I would be losing updates. So the solution basically is to do the following trick, okay? This is pseudocode. I get an array. I need to know the nodes, and I increment only the element of an array that is related to the node I'm on, and I ship it. Okay, so at source, I'm just incrementing the right element. And my merge operation is I'll calculate maximum for each of the slots. So if I got a direct update, and then if I got the update all the way around through the cluster, the maximum will be just increasing history. Okay, so it's just linear history will give me the right thing. And because I'm adding to this particular spot, I can just identify the spots and I'm not losing the count in the maximum operation, which means the final value is this. How I came upon this, I just read it in the paper and someone had to cleverly figure it out. This is how it worked. Like, people got the gset first. Gset was trivial. Then they distilled the right properties from gset, and they said, "Can we do counting?" Yes, but we need to think about nodes. And this is how the merge operation works for the maximum. So these are now the particular slots. So the maximum operation. There's a proof of correctness. The maximum will work. So if I got here the update that on node 1. This is the update for node 1. This would be just like a view of node 1. So from one side, I just got it got 1, but in the meantime, it got incremented to 4, and this node got 4. The final value disseminated will be 4, because this node gets the right one, this one will get the maximum, and this one's value of 1, which this node heard about, will get corrected to 4. Okay, how do I count with addition and subtraction? I need to create the PN counter, positive negative counter, which will have 3 operations: increment, decrement, get value. API is trivial, but the inner working is not exactly as trivial, because I can never subtract, because it's CRDT and subtraction is not good. So I have 2 values. One is positive counter and the other is negative counter, which they both grow. And at the end, before returning the value to the end user, I just subtract the negative counter from the positive counter. There is one problem with that solution, which is the overflow, because those counters grow forever, and that's one big problem with CRDTs. So one of the problems you've already seen, I need to know about the nodes. If my cluster is dynamic, which is the case for Akka, I need to devise a clever way of removing garbage associated with nodes. So technically it's called pruning. The other thing is I'm collecting garbage, and which means that if I incremented and decremented the counter, I still get 0. But in the meantime, I just get positive counter at 1 and negative counter at 1, which is not good. The other problem is I cannot have a global condition saying PN counter be greater than 0. Well, that's partly okay, because most interactions with the cluster would be with a single node that you can see in your region. So you'd have a session with that node. But suppose your session got broken because of some conditions, and then you get to speak to the other node. This won't work, because if I have the whole cluster, I could add 5 on one node and try subtracting 5 from the other node, but this is not possible because the other node hasn't heard about the update, so it doesn't know. There are clever ways to do that. So this, what I told you, is prevent decreasing if state on current node is less or equal to 0. But the clever way would be like ATMs, system of credits, escrow transactions. On every node there will be quota, and I would be synchronizing that quota out of band, and if quota needs to be increased, that would increase that quota, and so on and so on. And this is a way of actually synchronizing the whole cluster. And this is a clever thing which we can think of when talking about CIDTs, because CIDTs don't need technically synchronization, but global conditions need synchronization across the cluster. which is costly or even impossible for mobile devices. And if we implement CRDTs in a clever way, then we get a fine-grained way of thinking about consistency versus availability, so the trade-off. So my clever solution, which won't work for P counter, would be when decrement is not possible because the constraint will be violated, try to synchronize the cluster. But it might work for other operations. Okay, another clever object, which I will not get into details, is the observed removed set, or set. So this is a set which allows for removal of elements that have been observed at the current node. This is similar to P counter. You can only remove what you've added at the node or which you got informed about that the update has happened. So the other node needs to ship that. It's a global cluster property. Okay, so you cannot remove arbitrary elements. You cannot create a removal token that would be propagated through the cluster. And this needs version vectors for the merge operation. It's pretty complex, so I would not get into technical side. But this is possible, and with that we can get general maps which are indexed by those all sets. Right, the details are too complex. And, oh, this is the replicator, which does the LUB operation. Quite clever thing. If you think, because I'm a vintage guy, I think always when I look at that, I could implement it at home, okay? I also thought that, but actually in Akka it's like 3,000 lines of code. All right, so we already started speaking about Akka. So in Akka, if you'd like to use CRDTs in Akka, you need a top-level key to be able to access your objects. It's just a naming facility. It's just naming is one of the big problems in computer science. Okay, the operations using Replicator, and there is some cleverness in here. So get is very simple. You send to your local replicator, get me the object, identified by key, and you can supply a consistency level. This is a unique feature that akka-distributed data has. I can read local, I can read from number of nodes, I can read majority, which would effectively mean that I would get probably same state from the whole cluster. It works like that. I send a get message, get me counter one key, read local, or read anything, read majority, get me this key, and the cluster would reply either with get success, get failure, or not found. Okay, so get success, okay. Get failure, sorry, no bonus. Not found, the key doesn't exist at all. So it means that something is really, really wrong. Update works the same way. I could write local, write to end nodes, and so on. And update has an operation here, which is just a function. This is just add me one, add me hello, a string. So here we have objects which are, this is a P counter, this is a G set, and this is all set. So set and set. From this one we could remove, so we could ship an operation that would be a removal. Is that pretty obvious? Yes, there's a documentation for that, but you actually don't need the documentation. That's so simple. It's a very simple API, CRDTs, very complex implementation beneath. I think it's an excellent candidate for a library. Okay, and now shopping cart. Imagine that you have a shopping cart, and I think we will spend most of the remaining 5 minutes on this slide. Implemented in Akka, so a global shopping cart. And, well, adding items is trivial. You just add items to a cart locally, and they get propagated in the cluster. The items are identified by key. This could be ISBN for a book. And there are some additional properties of that. We are using here a last write wins map, so something maybe not optimal. There are some anomalies connected with that. But if instead of that we would be recording every instance of the item, so like if I want 3 books, I would just generate 3 entries, and the identifier would be unique identifier for the cluster, and I would just be counting. Then I could use OR set, and I would propagate OR set of books, and I would get rid of this actual problem anomaly because of last write wins. That would mean that update from the past with wrong clock might just break my state. So this LWW map is indexed with an OR set, and you know one thing about OR set, that if you want to remove something, it should be in your history. If it's not in your history, you cannot remove it. So I'm building a shopping cart for a cluster, and what do I do? When I want to remove something by product ID, which is the key, it is this ISBN, I first synchronize my cluster. And this is a cool thing which is missing from most CRDT implementations. I can synchronize my cluster. Maybe someone heard about this item being updated. And if they know about that, I just propagate to the whole cluster the removal of this. This is actually OSET operation, which removes all the elements. And this is going to be propagated very quickly because I forcibly synchronize the whole cluster. Suppose that this is for a local cluster running in your data center, and now someone told you you need to move it to them clouds for this to work globally. It's just a simple refactor away. What I would do is I would try removing this element locally. So I would just, instead of read majority here, I'm sorry, well, I'll try to read majority, and if I get success, just remove this object. And in case of not found, I would then do read majority and synchronize the cluster. Very simple refactoring, getting us out of hot path of synchronizing geographically distributed cluster of nodes and paying the cost of 200 milliseconds to get around the world. And from under law, you know that 200 milliseconds is going to be very limiting for your number of possible operations you could do. So if I have it, remove it. If I don't have it, synchronize the cluster. Cool optimization. Okay, now the interface is very simple. For gset, it's just I have gset. I can add an element, add 2 elements. This is not code running on a cluster, because for cluster I would need to use Replicator and send messages just for unit test maybe, so just an API. P Counter needs the implicit node on which it is running, just to mark the node. Now you know why, because it needs to mark the correct slot. The all set also needs to know about node and many other things. It actually needs the node to refer to the atomic version vector, which is Lamport clock running on this particular node, which we need for this instance, which is part of this 3,000 lines of code included in the replicator. But the interface is as easy. And all multimap is actually a multimap which indexes by strings, and in that case, well, holds ins. And we can add a mapping. We can add binding, which is just adding an element, and remove binding. And this is it. There's a couple of docs for Akka. So distributed data for 2.5. There are interesting specs showing you how to actually use that. So if you want to use it and you don't find it in the docs, just delve into source code. The specs are very easy to copy. I do it every time I need to do something in Akka. Interesting implementations from Akka samples, and there are interesting specs. This is, for instance, a shopping cart. The demo will not fit in the schedule. I'm terribly sorry about that. And the question is probably neither. Thank you very much.